Assalamualaikum everybody. Today we're going to continue on the non-uniform quantization of chapter 4, pulse modulation. Okay, so let me go to this full screen mode. Okay, so the non-uniform quantization. Okay, so one of the things that we already discussed before why we want to do non-uniform quantization, right? Okay, one of the reason is that, for example, for the weak signal, okay, so it will be represented by much more quantization level, okay, rather than using uniform quantization. If we're using uniform quantization, so this weak signal will be covered by much limited numbers of quantization level, okay. So non-uniform is to improve the signal to noise ratio. Q here is for the quantize of lower level amplitude, okay, just like weak signal, they have a much smaller amplitude, okay. So more level is available for low level amplitude compared to the high amplitude. So we were going to have a level of quantization which is more in the low level amplitude area compared to the high amplitude, okay, so that we try to cover the lower level amplitude. So the quantization level will be having more towards the lower level amplitude, and by the name suggests non-uniform means the quantization interval will not be uniform, okay. So increase in SNR, sinus to noise ratio for low level amplitude, and decrease SNR for higher amplitude. Okay, this one is logic because more quantization level will be focused on the lower level amplitude. So means that we will have a better SNR at this low level amplitude. However, the trade-off is that we will have to decrease the signal to noise ratio for the higher amplitude area, okay. So compending, by the word compending, is actually comes from compression and expanding, okay. So compending is to produce a uniform SNRQ for all input range, okay. So this is compending. Analog compression is done to the input signal before sampling and quantization at the transmitter. So analog compression, as we learned before, okay, let me do some sketching. Okay, we have sampling, we have quantization, we have coding at the transmitter side, okay. Of course, we will have similar opposite operation at the receiver side to retrieve the signal. So at the transmitter side, we will have sampling, we have quantization, we have coding, okay. So analog compression here is done to the input signal before sampling and quantization. So before here, so you're going to have analog compression, okay, to this input signal, okay. So let's re-end this show. Okay, sorry, I can delete. So we go to here, go to the first slides, okay. So this is basically the entire data communication system, data communication system. So uh, we just cover few parts of this, okay. So if you want to know more, you can explore on this, okay. So the compression is not shown here, but I want to show actually just now the compression, but there is no word for the compression specifically to show to you, but it is actually here, okay. In Okay, so we continue. So the analog compression is done before the sampling, okay. So expansion is done at the receiver. So if you see this, where we have compressed, so we will have the opposite operation at the receiver. Okay, just like we have uh, just like we have quantization, then we have dequantization at the receiver. It's mirror operation. We have mirror operation in order to recover back the signal. So expansion is happen at the receiver, and then compression is happen at the transmitter. So non-uniform quantization using mu law. Okay, so if you refer to the module, okay, sorry, let me get the module. Okay, so if you refer to the module, page 172, okay, so page 172, around this page, plus minus, okay, you will introduce to the A law and also mu law, okay. So mu law is a compounding algorithm that being used in United States and in Japan, okay. While A law is using in European, okay, using in Europeans, EU lah, okay. So if you want to discuss about non-uniform quantization using mu law, okay, so SNRQ equals to 10 log 3 over ln 1 plus mu square plus 6.02 n number of bits and dB. So this is non-uniform uniform quantization using mu law. Okay, so we will go to later detail about this mu law and A law. So I won't go here, okay, because it's covered in the later slide. So this is actually basically how you want to do the non-uniform quantization using mu law, okay. So I think the wording here, the formula is quite self-explanatory, okay. A mu is actually mu value is, for example, here, okay, mu value use is 255, okay, 255 for 8-bit system. So you need to see your bits for 8 bits, okay. Okay, so you may refer to example 4.5, okay, you may refer to example 4.5, please refer to example 4.5, okay, for the use of this mu law, okay. So this is what we discussed, okay. I go through quite brief in the class before we finish the class, okay. This is non-uniform quantization. So why we do it in the first place is we want to cover more towards of low level amplitude, okay, because the weak signal, if we are using uniform quantization, there are not many level quantization level to cover that weak signal. For example, for the weak signal, if we want to use uniform quantization, it's only be covered by 6, 7, and 8. Only be covered by 3 quantization level. But what if we are using non-uniform quantization? Then it will be covered by, for example, 5, 6, 7, 8, and 9 quantization interval, which is better, okay. So of course the disadvantage is that it will decrease the SNRQ of the higher level amplitude now, okay, decrease the SNRQ of the higher amplitude, but increases the SNRQ of the low level amplitude, okay. So expanding, compress, expanding a method used to produce uniform, okay, uniform S and R, okay, for all input signal range, okay. This is what we call this compending, okay, to produce a uniform SNR, okay, for all input signal range. Input signal is compressed at the transmitter and expanded at the receiver. So this is basically what is being done when we want to compress, what is compressed and what is expanded. Okay. So figure 70.3 is step in compending after Hofer and Martin. Let me see if this is shown in the module or not. So this figure is not available in the slide in the module. So hopefully that you know, I mean, it is not available. Is the photo is in the slide. So make sure you're well aware about this. Okay, so this is your input. This is your output. So as you know, we are going to do compression at the input, and we're going to do expansion at the receiver, inverse operation. Okay. So compending, compress, expanding. Okay. Analog compression is done at the input signal before sampling and coding, just like what I told you just now. And digital compression process is done after the signal is sampled. So there is difference. Okay. Just now when we discussed about compression being done at the input signal on the input signal for the analog signal, okay, for the analog signal, the compression is done before sampling and coding, okay, here, okay, the compression is done before sampling and coding. However, for the digital, okay, however, for digital, we still have this compression. However, this compression is done after the signal is sampled, okay. So you have for example, you see the analog. So you see the compressor. Okay, you compress the input signal before you sample encoding. Okay, before. This is analog to digital converter where the sampling process is started. Okay, for the digital, analog signal is input, analog to digital converter. Then we compress after. Okay, we compress it after it being sampled. So that is the difference. Okay, that is the difference. Depends on which type of compressor that you are using. If you use analog compressor, it will be before. If you are using digital compressor, it is after sampling. Okay, so different of compressor. This is not analog signal or digital signal. Is what kind of compressor you are using, analog compressor or digital compressor. Okay. So two populars of we do for this compending system, like I told you just now. You can refer to your slide, your module. Um, if you want to read from the beginning, is one from page 1 to 4. Okay, and of course it is up until around page 130 of your module. Okay, so you like we know brief just now. European, they are using a law, whereas USA, North Africa, and Japan, they are using mu law, in Japan. Okay, so let's we discuss on the A law. Okay, this one is actually for A law characteristic. Okay, so A compressor parameter, this A is the compressor parameter. You can see A here, A here, A here, and there. Okay, and X is a input. Okay, X is a given input. So if you refer to the module page 1 to 6, it mentioned there A is the compression parameter, yes, and in Europe, A is equals to 87.7 or 87.6. So this value is quite fixed, okay? For the European, they are using either 87.6 or 87.7, okay? An ALO algorithm is a standard comparing algorithm used in European digital communication system to modify the dynamic range of analog signal for digitizing. Okay, so I read the module wording because some of you didn't have the module. Okay, so this is the inputs in terms of modulus omega 1t, and then you have output in terms of omega 2t as well as modulus. So for European, they are usually using 87.6 or 87.7. Okay, why is an output? Okay, y is an output and x your given inputs. Okay, so this is your input, okay, x, and this is for your output, your y. Okay, okay, next for the mu law. Okay, mu law is using in Japan and US. Mu law is a standard compressed expand that is used in America and Japan. So the value of mu, like what I told you just now, is 255 for 8-bit for 8-bit system. So y is your output, and mu is 225 for 8-bit system, and x is actually your given input. Okay, so this is the same input and the versus output graph, and the value that usually being used for mu is 255. So you are referring to this curve. Okay. So for both law, the value of x and y refer to equation below. So x here is your input. Okay. EI is the maximum range. Okay. Is a maximum range. For example, if you have a signal, okay, in the range of 0 to 10 volts, okay, range of signal, 0 to 10 volt means the maximum will be 10. Okay, so this one is referring to the maximum of the range of the input signal. This one is referring to the maximum output range of the signal. So for example, if you have a case system that has signal in the range of 0 to 10 volt, so this one will be 10 volts. Okay, so NEI is actually the current given. Okay, the current given amplitude of input. Okay, for example, if the question say what is the output of a system given that the input is 0 and 7.5 volts. Okay, for a system that having range 0 to 10 volt, so it means we need to calculate two values. Okay, for this is 10, we know is 10 because the system maximum 0 to 10 volt. Then we need to consider what if our x, okay, sorry, not x, what is our EI. Okay, for example, what is given, let's say the time we have input. What is the output? What is the output if the system having input 0 and 7.5 volt? So first is 0 over 10. Okay, then you have 0. Then the output y equals to log, okay, 1 plus mu x, sorry, very difficult using this, 1 plus mu x over log 1 plus mu. Okay, let's say what is the output for a system given that the input is 0, for a system that having range of 0 to 10 volt. So means maximum is 10 volt, EI max 10, and for given input is 0, so that's why 0. So EI equals to 0 over 10, we will get 0. Then so this is your x, okay, EI over EI max. So because this is 0, if you put 0 here, okay, 0 times by mu use, which is 255, so you result in log 1. Log 1 is 0, right? So whatever 0 divide whatever will still become 0. So your y will be 0. Means that for a system having range of 0 to 10 volt, for a given input of 0, it will produce output of 0, okay, based on the Mueller compounding algorithm, okay, something like that. So you can refer to example 4.5 for the example in the module. Okay? So example here, next is example 4.3. I think this one is also should be coming from the books, okay, but the number may be different. Okay, so a compressed expense system using mu law, okay, which is mu equals to 2.55 pip, is used for signal with range 0 to 10 volt. Okay, so this one is actually example 4.5 in the module. You can refer to the module. Determine the output of system if the input is 0 and 7.5. So I already briefed just now. What for the 0? So you try on your own. Okay, what is y if what if y what is y output if ei is 7.5. Okay, you try to do it first. Okay, of course the answer is down below. Okay, I'm not sure if you have this answer hidden from you or not, but I think not, because this one is other, but if not, you can refer to here, okay, because it's recorded.